I tell you today, I have other pencils, but I don't have graphite for them. I've used them all up. Fine.
Yeah, well, it's a pleasure to welcome Sarang Gopalakrishnan. Go ahead.
Well, I can't either. It's fine. That's fine.
Princeton University, and he's going to teach us how to learn.
Yeah, it's optimistic. Yeah, so it's a great pleasure and honor to be here. I was last year about 10 years ago as a student. You know, I remember a lot of things from back then, but the one thing I remember the best was when one of the speakers went off to the men's room with his microphone connected. And so when the guy offered me a microphone right now, is like, no, I'm not gonna, whatever I do, I'm not gonna do that. So anyway, yeah, no, I mean, it was, you know, and the mic was live, right? So it was really vivid and unforgettable. I'm surprised you don't remember it. You were there.
I remember it, but I don't
Yeah. Anyway, yeah, so slightly more serious note. So my lecture plan, which may or may not have much relation to what actually happens, is to talk about, you know, how you get information out of a quantum system in sort of 3 stages. First, you know, where's the information? And that's what I'm going to talk about today. Second, I'm going to say, and that's going to bring us to the connection between the StatMech stuff we heard about, or you have been hearing about in Raman's lectures, and the error correction stuff you'll be hearing about next week. So it's sort of a bridge between those 2 things. Tomorrow, I hope to talk about ways of getting information out. And that's the province of these transitions and learnability of quantum information from classical measurements. And Friday, the plan is to talk about, well, okay, you've got the information out, now what do you do with it? And that's to talk about things like using measurements and feedback to prepare quantum states that wouldn't exist without those resources, or, you know, wouldn't exist on those timescales with those resources. So that's where we're going. And to begin, I want to say a little bit about error correction. But I want to talk about it in a very zoomed out, high level way that doesn't specifically reference any actual practical error correcting codes or anything like that, because you'll hear about those next week. I just want to talk about error correction because error correction is about protecting quantum information. And one of the essential questions you have to ask in order to do error correction is you have to ask where the information is. Okay, so a very quick reminder of how classical error correction works. So for example, you have a bit, and you want to protect it against bit flips. And so what you do is you copy it a few times. So it goes to these 2 words, or these 2 strings of length 3, but they could be longer if you wanted them to be. And these are called code words. And the key thing that makes it work is that most 3-letter strings are not code words, right? So when something happens to a code word, it becomes not a code word, and then you realize, okay, something happened. Can I fix it up? So, so an error happens, for example, and then, for example, if you had, let's say 0, it goes to 000 after the coding, and then one of your bits flips, and so now you have not a code word. You have a thing that has an error in it, and then now what you want to do is you want to undo the error. And you say, okay, I look at this guy, you know, was it likely to have come from 000 from 111? And so, if I assume that I have an independent error model, then it's kind of obvious what I should do. I should take majority vote. And that'll mean I flip it back down to 0, 0, 0. And so that means that I recovered from the error. I could use my measurements of the state to figure out what the error most likely was and to recover from it. Okay. Okay, so this procedure that I wrote down works fine as long as the error only acts in 1 qubit. But of course, once the error acts in 2 qubits, you're a bit hosed because you don't know where to send it back to. So that's one very important aspect of classical error correction. In order for it to work, you need to have the following physical picture. So you have a code word here that's, let's say, 0, 0, 0, 0, 0, and then you have a code word out there that's sort of far away somehow in the space of words. And what the errors are going to do is they're going to act sort of there's a natural metric on the space, right? The metric is just how many places are 2 strings off in, right? And what you say is that errors are going to sort of spread this guy out over some distance in the space, and this guy's going to go out to some distance there. There's some radius of strings that I could have gotten from the code word by applying errors. Okay, and the key thing is as long as these spheres don't overlap, I can do error correction because I can just say, okay, which was the closer string, and I can go to that, and I can just do the decoding based on that, right? So, but of course, once the spheres start, if my errors get more pervasive and bigger, then my spheres begin to overlap, and I have some region over here where I don't really know what to do because this could have come from either place, and I don't really have a good way of distinguishing where it could have come from.
Can you say,
yeah,
say quantify it, like if that overlaps a small fraction of the total sphere volume or something?
Yeah, so well, it's not. I'm talking about recovery with fidelity that like goes to 1 in some appropriate limit. So when I have a lot of words and a lot of tries, and I want to ask, am I going to succeed with probability that like converges to something close to 1 versus something that fails with a finite probability? That transition happens when the spheres begin to touch. But that's the rough intuition you should have. And the reason I bring this up is not, but I mean, okay, there are a couple of reasons I bring this up. One of them is to introduce this idea of code distance. So in this classical perspective, the code distance in this case is just the Hamming distance between code words. And so Hamming distance is jargon for number of spots where they're different. Okay, so the code distance, Hamming distance between code words, and as long as the code words are far enough away from each other, then that means that for at least error models that are local in the space, as long as the errors tend to corrupt less than half the Hamming distance between 2 code words, you're okay. So for example, if you're in my original code, the Hamming distance was 3 between the code words. And so I could correct errors in 1 qubit or in 1 classical bit, but not in 2 classical bits. So that's the notion of code distance. It's it's a simple thing to compute, and it gives you a rough and ready way of figuring out, am I likely to succeed in correcting errors? Okay. And the key thing about this entire philosophy of thinking about error correction is I don't really need to think about an explicit recovery procedure, right? I can just say, okay, these guys are far away in Hamming distance, and as long as each code word's images are different than every other code word's images, there's in principle no confusion. Though of course, if I have a complicated code, actually performing this recovery procedure of finding the nearest code word and going to it might be quite complicated. In principle, it exists. And that's sort of the only question, the only aspect of error correction that either classical or quantum that I'll be thinking about today. Right, are the errors sort of, are the erroneous words still sort of sufficiently close to the original words you can pull them back or not? Okay, so that's classical codes. And again, you know, do interrupt as I go. Good Lord, what is this? I was talking to Matthew about modern art on the way back from lunch. Like, okay. Yeah, it's at least less structured. Okay. So that's the classical case. And now what I want to do is I want to talk about the same set of concepts, like their applications to the quantum case. It should be you should see it as a fairly straightforward extension. But I do need to introduce some concepts now that you might have already seen, but I guess it doesn't hurt to see them again. So first I need to talk about some jargon. One important piece of jargon is this word isometry, which you may or may not have seen. So a unitary operation is a one-to-one map that preserves inner products. An isometry preserves inner products, but it goes from, let's say, Hilbert space 1 to Hilbert space 2. And it has the property that that I dagger I is the identity. So let's say this is you want to think about this guy as a small Hilbert space, this guy is a big Hilbert space. And so I takes me from small to big, I dagger takes me back from big to small, and what I end up with is where there's the identity on the small Hilbert space. Okay. And so what is an isometry in practice? So in tensor network notation, I send in my space H1, and I introduce some reference qubits, some additional qubits that are initialized in a fixed state like 0. And then I apply a unitary on this full thing, and this gives me, and this entire object is the isometry. Okay. Now you'll see that if I take this isometry, that's U, and then I act U dagger, you'll see that this in fact is the identity, right? Because the U and the U dagger cancel, and I end up with the identity in the smaller space because these guys just decouple completely. Yeah, go ahead. You can think about, so I would say that some purifications are isometries. Yeah, so I guess if you think about, yeah, no, I would rather think of purification as a map. Yeah, I guess you could think, yeah, would it be an isometry if you, so I guess if I were to think about purification as an isometry, I would say, okay, here's my original state. And then let's say I want to do the Choi map, and I want to treat it as, yeah, no, I don't think so, but I might be wrong about this. I haven't thought about that. It seems to me it's spiritually, it's a bit different. But for example, you know, one thing I'm going to talk about is when a system interacts in an environment, that's an isometry, because the environment starts out in a reference state, my system interacts with it, and now I have a state in the full system and environment. So the purification of quantum channel is an isometry, but I'm not so sure about the purification of a mixed state. Okay, if anyone has the answers to questions I'm asked, like please yell them out, because I would like to know the answer to. Yeah, correct. This is a map. This is just a map from, it's just rectangular matrix. It's a rectangular matrix that's got this restriction on it, right? That's what it mathematically is. But yeah, so physically you want to think about it this way. So you can also see, by the way, that if you tried to arrange these things the other way around, you wouldn't be able to cancel out the U's and the U daggers, because it wouldn't be, then you'd have like the projectors in the way, okay? So this only works one way, not the other, whereas unitaries, you can contract them both ways. Okay, so yeah. Oh, what do you mean? So the isometry is I. So this is not the identity, right? This is, sorry, I is just some letter.
I mean, if there exists a matrix P times I identity, whether let's call it isometry or it have to be I dagger times I.
This is a condition for a matrix to be an isometry. So you take the matrix, you multiply it by its adjoint, and you get the identity. That's the definition. And in practice, this is the picture you should think about when you think about isometries. Okay. Okay. So that's what an isometry is. And so that's one bit of jargon I wanted to get out of the way. A second bit of jargon I wanted to get out of the way is what a quantum channel is. And I sort of started this out already. So by the way, you can see why I'm talking about isometries, right? Because in analogy to the classical case, I want to take my small code space and embed it in a much bigger space. And I want to do so in a way that is as close to being to preserving whatever structure I had as possible. And so the natural way to do that is via a procedure like that, right? Okay, so that's what an isometry is. And a channel is, in terms of this, I already said what it was a little, to some extent, in my response to Leo, but the way you think about a quantum channel, about any quantum channel, is that you can say that here's your system, and here's your environment, and the environment begins in some kind of reference state that you know. It doesn't have to be the zero state, it doesn't even have to be pure, but let's say it is for now. And then you apply a unitary, and then something happens here. This and whatever comes out is this state is a state in the system plus the environment. And normally, what you say is that you don't have access to the environment, so you have to perform a trace over the environment to get a map from the system to itself. Okay, that's the evolution of an open quantum system. So so that's U, and then I'm going to do a U dagger on the bra side. Let me do it. Let me put the. So once again, this is the environment. This is the system, and I have to throw away the environment. And the way I do that is by performing a partial trace over the environment. And so this, you'll notice, gives me a map from density matrices on the system to other density matrices in the system. And this sort of legal map from density matrices to density matrices is called a quantum channel. Okay. Now, any channel, given the structure, and Raman talked about this, I think, as well, but let me say it again. So whenever you have a leg like this, you can break the leg at the cost of including a complete set of states. So the channel can be written by breaking this leg and introducing a sum over states in this way. And the physics of this is that what's happening here is that that you have a system and an environment. But now I'm going to think about the system as Alice and the environment as Bob. I'm going to use that notation. I'm going to use that terminology a lot throughout this lecture, but just want to warn you of it. So yes, you have system and environment. They interact. And then Bob, that's the environment, makes a projective measurement in some basis. Okay, so that's what this process corresponds to. And this thing, this sort of piece of a channel is called a Krauss map. And it's indexed by the measurement outcome that Bob got from his measurement. Okay, and to get the quantum channel, what you do is you say, okay, Bob made a measurement, but then didn't communicate the outcome to Alice. So Alice has to sum over all possible measurement outcomes, the appropriate weights, and that brings you back from here to there. Okay, so you can think about a channel either in terms of this picture or equivalently in terms of this picture where you perform a measurement and throw out the measurement outcome. So that's if you like what the channels have to do with measurements, and then so this I can write in this way as Krauss map acting on rho yeah, sorry. So if I normalize these states, there would be weights P sub k. But I guess Raman talked about this morning. It's convenient not to worry about normalization. So this diagram consists of this wave function is not normalized. The norm of this wave function is the probability of this measurement outcome. So I could normalize it and divide by the probability, but I'm choosing to work with the unnormalized state because it's sort of manifestly more compact. Okay. Yeah.
The sum just has traces to one. You're saying it's the individual terms not.
Yeah, the individual terms not normalized, the entire, yeah, precisely because the entire thing's got to add up to one. Yeah. But the norms are sort of buried in there in the sort of in the weights of the norms of these guys correspond to probabilities. Okay, so that's what a quantum channel is. And so okay. I had okay, I'm gonna move over here now. So I just need one more bit of preliminary jargon. So I was going to say a few things about purification, but I feel like after Ehud's lecture, we have like heard quite enough about purification for today. So I'll just use it and take questions if you have them at the time. But okay, so the last thing I want to say is I want to say a couple of things about mutual information. And so mutual information for two quantum states is defined as and I think that that you've probably seen a lot of this, for example, in Tarun's lectures over the past couple of days. But the mutual information is a simple way of detecting correlations among different subregions of a state that's globally mixed in principle. And so one thing I want to say about mutual information is the following very important fact. So the fact is that the mutual information of with a subsystem consisting of, say, BC is greater than the mutual information of with a part of the subsystem. So this is something that should be intuitively obvious. You have more correlations with more stuff, and you throw out information, you lose mutual information. Actually showing it mathematically, though, is remarkably hairy, that to be related to the strong subadditivity of entanglement entropy. So it's actually annoying to show, but I'm just going to treat it as an obvious fact. So this fact about mutual informations has a consequence, which is that if I apply a channel to B, this is just some channel, then I reduce the mutual information. Okay, and this is called this is sometimes called the quantum data processing inequality. So this, yeah. No, it's just a channel that's acting on B. It's just some map. It's just some super operator acting on from B to B. Okay, and so it should be clear that that this thing that this fact is that obvious to people? Does anyone want to tell me why it's true? Yeah. precisely, because this thing, to compute this thing, what I did was I took B, I enlarged it to BC, where C was the environment, and I traced out the environment. So that means that when I apply a channel, I'm gonna on a system, let's say I have mutual information between two systems, and I apply a channel to one system, it's going to degrade the mutual information. And that's sort of a very general property about the evolution of mutual information under channels. Okay, so right. So now let me going. Okay, so now I'm set up to discuss what it means to talk about quantum error correction in this sort of very general way. So I have my system, which I'm going to call in sort of an analogy of what Ehud was talking about. It's going to eventually be the reference, and so this is my this is a small space. And what I want to do is I want to protect. So you want to protect states in okay. And so what you do is you embed via an isometry in a much bigger space. Which is the physical space that's encoding your small qubit, like your few qubits. So you isometrically encode this guy in Q. Okay, once you encode it, and so this is I don't know. Let me say that I have rho in R. So this maps isometrically onto rho twiddle in Q, and now an error X. And so that an error is a channel from Q to Q. And once the error is acted, I now have some sigma in Q, which is not rho twiddle, right? And so if the error is correctable, then I have a recovery channel. No, it's important. The recovery is also a channel. It's a physical operation that that I can perform. The recovery channel goes from Q back to Q, and the idea is that you want to be able to go back from sigma to rho twiddle. And note that this is not, this would not be possible for arbitrary states in Q. That would not be realistic. A channel cannot be inverted like that. But the point is that it's got to be true for like any code word. So any rho twiddle that came from the isometric embedding is recoverable, but most other states in Q just get degraded into something else. Okay, but I don't care about those because those are not protecting the quantum information that it is my intention to protect. Well, I mean, from my perspective, it's very the words in R are very special, right? Because those are the ones I want to protect. Yeah. So it's just saying that there exists. It's like there exists a subspace of Q such that this can be done. Okay. Yeah. This is what it means for the error to be correctable. So if this were not true, then I'd just be hosed. But for the error to be correctable, this has to be the case. It's what it means to do error correction. It's that you have your subspace, and in that subspace, you can sort of undo the action of the errors. Okay? No, in general, you're not. I mean, in general, if I just try to apply like isometries in like arbitrary ways, I am not going to get an error correcting code. Yeah. Okay. So yeah.
You want it deterministically or with high probability?
I would like to, for now, insist on it deterministically. But in fact, most of what I say can be made approximate. And you make it into high probability. With high probability statements, you have a high fidelity, yada yada. I don't want to do that because going down that route will involve a lot of 1 norms and 2 norms, and I just want to spare you some pain. Okay. Yeah. Yeah, precisely. So the redundancy in this case, I need redundancy, right? Because otherwise, anything that happens has to, this is not going to work in general for the full space. So I can only hope that this is possible in small subspaces of the full space. And so in order to do that, I need to have only a small part of my Hilbert space be encoding quantum information at all. And so yeah, to do that, I need the isometry in the first place, just like sort of spread the information out. Okay. Okay, so that's error correction. And now let me say okay, so let me make a very quick comment on what error correction has to do with the purification perspective that Roman and Ehud both introduced, and then I'll move on to talking about sort of a more formal discussion of error correction. But right, so so if I have ultimately what I want to do is I want to preserve arbitrary superpositions of quantum states in my code space. So if I had an error on a particular unraveling, if I can always write the error in terms of this picture where a measurement is performed, the measurement outcome is thrown out. So I can just take an individual trajectory where measurements are done. Okay, that's a Krauss map, and so I can say, okay, fine. So I have, let's say, a psi and a phi in my code space. And so I want to make sure that the error now acts as, and so these are going to map on the isometry to, okay. And so when my error acts, it's going to act as, let's say, a single Krauss map. It's going to act as MK on. And so that's what's going to happen when on a single trajectory of the error acting. So so the system interacts with the environment made a measurement. Okay, and I want to make sure that that the structure of superpositions of these guys is unchanged. And so I need both of these things to basically shrink all vectors down by the same factor. If I distort the inner product between psi and phi, then I've lost. If I just collapse into psi of phi, then I've also lost. Okay, so I need these things to, I need that MK of psi twiddle is equal to MK of phi twiddle if these two guys are initially normalized. And I also need to make sure that that the inner product between these is preserved. Up to, it's proportional to, so there's an overall normalization factor, but which doesn't depend on the states, but and so if these conditions are true, if I'm in the code space, then I can create a mixed state in the code space, and the measurements that I perform are not going to be able to purify the mixed state. Okay, so if there were a code space, then my measurements would not be able to extract information about the code space, which makes sense because they were able to extract information about the code space. They'd be able to collapse the wave function, and then it wouldn't be a very good code space. So that's one basic intuitive consideration with a code working, and you can see it's very closely related to this question of like, if I send in an initially mixed state, I make a bunch of measurements, does the state remain mixed or not after the measurements? If I'm in a code, then it better remain mixed. Okay, so right, so that's all preliminaries. And so now what I want to do is I want to introduce an important result about codes. That's called the decoupling principle. Yeah.
Why do the norms need to be?
Because otherwise, I would have learned which way information. So I'd have taken the superposition of a half of that and half of this, and then I would like apply the map, and then I'd have more of one than the other. So it's obviously a different state, like not. Okay, so okay. So what I want to do now is I want to introduce a result about how you can think about this idea that the environment should learn nothing about the code space in order for error correction to be feasible. So okay, so let me draw once again schematically what we're doing. So we have a map from row of a density matrix in R through an isometry. So now it goes into Q. And then I have an error acting on it. So it's like this is rho twiddle, this is sigma. Okay. So this is the isometry that encodes the state. This is the error channel. And what I want to do now is I want to purify everything, just like Ehud did in his lecture. And so let me do that. Yeah, let me actually do that here. So I'm sorry, I'm going to sometimes draw my circuits vertically and sometimes horizontally. Yeah. Sorry, there isn't a Q twiddle. Yeah, it's just Q. Sorry, yeah, there wasn't supposed to be a twiddle there. Thanks. Okay, so when I purify things, I can think about my initial state. Okay, let me actually just delete this because I don't really need it for anything downstream. That was just a remark. Okay, so what I'm going to do now is I'm going to begin with a purification of the state of. So I'm going to introduce the purification. So instead of having initially mixed state, I now have a pure state in a bigger Hilbert space. This is the square root of rho or something like that. And so now I apply an isometry that enlarges my space. So this entire thing is a map, and so now it lives in Q. And then now what I want to do is I want to introduce the error, but I introduce the error just like I did with quantum channels before, by introducing by adding in some additional degrees of freedom, applying an isometry, and at the end of the day, I have 6 legs that come out. These legs belong to Q. These legs belong to the environment. Okay, and so why do I want to do this? Basically, because what I want to talk about is I want to talk about the structure of entanglement on this final time slice. And so in order to be able to do that sensibly, I want to have an instantaneous, well-defined state on the reference, the system, and the environment. So just to say it a different way, what you really care about is somehow about the fidelity between the input and the output in these questions, but that's an annoying thing to define because not instantaneous, and entanglement measures naturally live on the same time slice. And the simplest way to make it instantaneous is by a purification trick. Okay, so that's why I'm doing this. Okay, so this is my state on the reference, the system, the encoding system, and the environment all at once. And what I want to do is I want to talk about the entanglement properties of this state. Okay. If I trace out the environment, that's my quantum channel. But right now, I'm not going to trace it out because I want to talk about how much information is in it. Okay. Right. Okay, good. So that's the setup I need to state the result, which is oh, sorry. Yeah, this is square root of rho. So when you, yeah, so if you know how the Schmidt decomposition works, you'll see why there's a square root here.
Isometry is not a quantum channel.
An isometry on its own is not a quantum channel because just a map from a smaller space to bigger space that preserves inner products. The quantum channel doesn't really do that, right? Because an isometry which does it followed by a trace, which is kind of a destructive, irreversible operation. Yeah, exactly. You're going back down from a bigger space to smaller space. And in the process of doing that, you're inevitably gonna like throw something out. But the important thing is that if you do it right, you're not going to throw out the stuff you care about. Yeah, sure. Okay, so let's talk about let me put that let me make a little colored box for it to keep it separate from the other stuff. So okay, let me imagine that I had some state. I had some pure state on 2 qubits. Okay, so it's got some coefficients. It's this tensor that I'm sort of writing down with 2 indices because I've got like 2 subspaces. And now what I do is I compute the reduced density matrix on one side of the system. And in order to do that, I perform this partial trace, right? And so this object is rho, and yeah. So if you like, so now what I want to do is I want to take the state and then write it down in such a way that if I perform this multiplication, so if this is square root of rho, and this is square root of rho, and you trace the matrix multiplication this way, you get a rho back out. Okay, does that make sense? I forget who asked the question. Is that okay? Does it make sense? Okay, great. All right. So yeah, I promised you a claim. So let me go and boldly claim it. And so the claim is that exact is possible if there's no mutual information between the reference and the environment at the final time slice. Okay, so I've got this full state and everything, and I compute the mutual information between the reference, the reference and the environment. And if there is no such mutual information, then error correction is possible. That's the claim. Yeah, yeah. You can, because so I'm not gonna try and do it in real time because it's a bit annoying, but like you can take this thing and show that like this is well, the thing that's easy to do is to show this is invariant under all the ways of dilating a quantum channel. So you can pick your way of dilating a quantum channel arbitrarily, and this will be true. But you can also rewrite it like less transparently in terms of properties that are purely properties of the map from Q to Q.
I guess I'm trying to understand like what property of a quantum channel is this? You have many quantum channels.
Yeah.
Depending on how much environment entangles with your
isometry. Yeah. But
some of them correspond to this.
Yeah.
What restriction is it on the channel?
Yeah, the restriction to the channel is something like this, right? What it's doing. Okay, let me give you an example of a case where this works and a case where this doesn't work. And so in both cases, I'm going to consider a quantum channel that that's very simple. It just consists of swapping in a qubit in a 0 state. So okay, here's an example where it works. So I have my isometric embedding of the qubit that I care about. and I just embed it trivially using the identity map. Okay. So now I've done my isometry. Now my error is going to consist of taking a 0 straight from the environment and swapping it out system qubits that had nothing to do with the reference. Okay, so this guy is using dissipation, but it's not touching the reference. So in this case, the mutual information between reference and environment is manifestly 0, right? And an example where like that's not true is if I did the same thing, but now I just moved this guy over, and then okay, now the environment comes in, swaps out, and now bell pair has gone into the environment. So that's the phenomenon we're talking about. It's like there's information about the reference, and there's information that the environment is extracting in the process of like performing the quantum channel, but you want those to be different things. You want those not to coincide in any way. I mean, so I think these examples are probably about as clear as I can make that picture.
But if I write these in terms of cross operator, like what, like if you didn't state it in terms of a state,
Yeah.
is there some diagnostic?
Yes, I mean, you can sort of say you can check if your Krauss operators for the channel do the thing of preserving all inner products. And in fact, there's a stronger thing because you need to figure out where the error happened in order to correct it. So you need to preserve inner products. You also need a couple of other conditions known as the error correction conditions. I think I don't want to go into those because they're sort of slightly, to me, less intuitive than this information theoretic picture. So a key point I want to make is that different ways of dilating, there are different ways of extending a quantum channel in this way. But fundamentally, every dilation of a quantum channel has the same entanglement structure, because otherwise it'd be a different quantum channel. And so this is sort of, it looks as if it's specific to a particular unraveling and a particular purification, but in fact, it's not. They're all the same up to like local unitary operations entirely here, entirely there. So don't change the entanglement structure. Yeah.
In the reference here, the additional Hilbert space to purify the.
Yeah, correct. That's right. Yeah. And so, so it's like Ehud said, right? So you take your initial state and you purified the reference. You need to think about it as a mathematical device. Or you can really say, okay, so Alice and Bob have this shared, bell pair that's a resource. And then Bob is trying to protect it against decoherence into the environment. And you can ask, at the end of the day, do they still have their bell pair or not? Like that's a perfectly reasonable, like physical picture of the entire process. And so you can just take that as fundamental. Yeah. Yeah. Yes. I'm not claiming that's quantifying entanglement. I'm claiming that it's being 0 is necessary and sufficient for this procedure to work. And that's because, I mean, even getting classical information about the reference and leaking it into the environment is going to destroy my ability to recover the state. So I don't need to make that distinction for the purposes of this argument. Yeah.
Just to make sure, for the statement to be true, is it necessary that R, Q, and E globally is pure?
Well, it is in this situation. If RQE weren't globally pure, that's because you haven't introduced enough of these. Just put an E prime, and if that fails, put an E double prime.
But again, like, you have some entanglement
Yeah.
between R, that delta.
Yeah.
You just don't want the environment to entangle your system.
Yeah, exactly. Yep. Yeah, that's really all that you need. Yeah. And so, so the fact you need this one direction of the claim should be completely uncontroversial, right? I mean, if the environment's learning about your reference, then you're definitely not in a bell pair between the reference and the system. It's maybe the opposite direction that's like a little more non-trivial. I'll come to that in a minute once I'm done. Yeah.
Yeah. A very restricted example. In principle,
yeah,
you want to also cover cases where there's non-trivial unitaries.
Yeah.
Space.
Yes, absolutely. Yeah.
And so then it's not like so clear where the extra qubits you introduced.
Yeah.
In new isometry. So distinct from the one that.
Yeah, in fact, these are in general going to be very non-local subspaces that it's very hard to think about. But the question is, are they overlapping subspaces or orthogonal subspaces, more or less, right? So that's, in this example, it's obvious which they are. In general, you would have to compute this quantity to figure it out. So if yeah, the point is that quantity captures it, and so, you know, okay, so I'm kind of just make one statement, getting a bit ahead of myself, but like this quantity is a thing that is very natural to compute in stat mech models, because just a matter of entanglements, which you can like write in terms of all this domain wall stuff. So once I've gotten to this result, then that sort of opens the door for like using stat mech ideas to talk about error correction. So this results to the bridge that connects that stuff to the stuff that we know how to do, at least in random circuits. Yeah.
What exactly is big Q?
Big Q is a Hilbert space that contains, in that example, for example, 3 qubits.
So the diagram of Q is just labeling subsystem.
Yeah, it's a subsystem consisting of 3 qubits.
And why does Q appear as another thing in the horizontal?
Oh, sorry. I just want to, I'm just trying to label which Hilbert space these wires belong to. That's that. I'm just trying to make clear that single lines are R lines and double lines are Q lines, something like that. I just need different notation for different Hilbert spaces. Yeah, if I writing this in a paper, I would like use different colors or something. Yeah.
This thing,
Yeah. Yeah. Yeah, that's much less restrictive. I mean, let me throw that open to the audience. Does anyone know? I don't know of a simple criterion like this for that. Because certainly, you know, your environment can learn something about your system, and then you'll have to, and then you look at the system and you're like, aha, the environment learned something about the system. So that's really more like saying that there are some measurements you can perform on your system that'll give you particular outcomes when there's no errors, and some other outcomes when there are errors, right? So that's not easily reducible to this.
the errors overlap.
Mhm. Yeah, that's right. So if you think about it in terms of Hamming distances in the classical example, for example, the factor of more or less 2 between correction and detection, because you can detect the error even if your spheres almost completely overlapped. Yeah.
It's very intuitive that if we want the information in the initial set, we send into the encoder to leak into the environment.
Yeah.
But how to integrate understand we don't want information on the reference with the artificial filter space we use to purify the state to leak into the environment.
I think I would take the perspective that I was like giving in my answer a little while ago, which is a perfectly legitimate way to think about all of this, is you're trying to protect a bell pair. Okay, so you have a bell pair between Alice and Bob, and Bob is subject to noise. But you want the bell pair to be a good bell pair in the sense that it can be used for like in the sense that it carries entanglement, be used for teleportation like tests. So from that perspective, it's natural to say that you want the reference to remain.
Oh.
Yeah. So that's the perspective I'd take for that. Okay. So I think let me actually now quickly sketch why this statement is true. So one direction is, I think, so clear intuitively that I'm not even going to argue for it, which is that that if this is not true, then okay, well let me make that argument. So there's the simple direction, which is like suppose I of reference with the entanglement is greater than 0. Now let me compute something which is the sum of these two guys, and so you know you can do this. It's SR plus SQ minus SRQ, which is SE. Does everyone see that? Oh, you literally don't see it. Yeah. Okay, so Is that working right now? Okay, so this is there's the sort of there's 6 terms here, right? So I'm gonna write them out. Plus SQ minus SRQ, which is SE. That's clear, right? And then you add this other thing, which is SR plus SE minus SQ. Okay. So this thing is just some constant to do with the size of the reference space. And so if this guy goes up, then this guy's got to go down. Okay. If this guy goes down, then by quantum data processing, there's nothing I can do to bring it back up. And so there's no way to do error correction. So that's this direction of the argument. That's the simple direction. Now let me go to the non-trivial direction, which is suppose this thing is 0. Then okay, I guess I didn't actually write down a proof of this, but I'm just going to quote this result. Then rho on it's basically saying if there are no correlations between R and E, then this must be the case. Okay, and so this means that I can write rho of reference and the environment in terms of joint eigenbasis as Ri Ej okay, just saying this is just writing out a product density matrix in its eigenbasis, which exists because a density matrix summation operator. Okay, so now what I can do is I can construct up to unitaries on Q the Schmidt decomposition of the state on the full system, which is going to be okay. So this is the Schmidt decomposition of the full state that if you then traced out Q, you would get that as a density matrix in RE. Schmidt decompositions are unique up to unitaries acting on Q, which are going to be part of my error correction protocol. So I'm okay with unitaries on Q. So I can write this down in this way, and now the key point is I can construct in terms of this guy an explicit recovery channel, which okay, I guess how am I going to do this? Well, let me migrate it over there. I don't want to hide that. And so the key intuition behind what this recovery channel is it's really, there's the sort of the system, the system, each Schmidt state of the system knows separately about the reference and the environment. And so in effect, what you can do is by choosing your measurement basis on the system on Q correctly, you can just figure out what environment state was found without knowing anything about what reference state was found, because the factorization of these Schmidt coefficients. So sort of in equations, what you can write down is you can write down a set of projectors that look like sum over I Qij, Qij. So notice that I is my index belonging to the reference, and J was my my index belonging to the environment in the previous expression over there. And so this is just basically saying, this is basically a measurement on the system that just plucks out for me what state the environment was in without collapsing the reference at all, given that the global state has that structure. Okay, and so notice that this is the sum of these is a full projector onto everything, and so this is the proper. So these guys define a complete projective measurement. Okay, and so now let's say that I hit the global state, one of these guys. Then what I'm going to get is I'm going to find that so pi j psi is I'm going to pull out EJ, and I'm going to get a sum over I of Ri. Okay, so that just comes from applying that projector to the state, and so now I'm basically done, because now this thing. So I've preserved the density matrix on R, because the original eigenvalue is that density matrix of the RIs. This guy's got the same eigenvalues, so it's just some purification of the reference density matrix. Because every purification of the reference density matrix is the same up to a unitary on the system, I can just apply the relevant unitary on the system and recover the initial state. So that establishes that that I can do this. And so whenever the reference, the environment decouple, that's sufficient for me to be able to construct, in theory, an error correcting unitary, although actually finding this unitary is highly non-trivial in general, because you need to know the Schmidt decompositions. And so I'm not saying this is like a computationally feasible way of actually doing anything, but it's just a proof that that in principle such a unitary exists, and the only task is to try and find it. Okay, yeah. Yes, because that's how the Schmidt decomposition works. Well, so well, I mean, it's sort of you can always restrict. So the way the Schmidt decomposition works is that you only have, so if this thing has some rank, then there must be at least as many states of Q as to maintain that rank. Then because RQE is pure, that's guaranteed. Otherwise you wouldn't, otherwise you'd have like non-trivial eigenvalues on RE, but they wouldn't correspond to anything because the world wouldn't be pure. So from the fact the world is pure, the existence of a sufficient number of QIJs is guaranteed. Yeah.
So you wrote rho RES as a product of rho R and rho E.
Mm-hmm.
What if I take rho RES, something separable?
Does
it mean that you can do that?
I doubt it. I have no idea what you can prove in that case. Again, like if anyone in the audience knows the answer, please volunteer it. But I don't think there's anything simple you can say about that case. Yeah.
You said about the last step.
Yeah.
So I get the state after the projection.
Yeah, you're happy with this. You're happy with this guy. Yeah.
This guy.
Yeah.
Like, why can't I just now have my state?
You have your state. Well, the point is, well, because QIJ is not really the state that originally, let's say, yeah, the initial state you encoded into here was in a totally different basis. So QIJ was a Schmidt basis I constructed by the Schmidt decomposition of like this state in RQE. All I know is that this state has the same reduced density matrix on R as my initial state that I encoded, but it could have been rotated by some like completely arbitrary unitary. And so that's the hard part, because that's the decoding map that I don't want to talk about, but the decoding map is the unitary that takes this guy back to the reference state that I know and recognize as being the encoded information. Okay, so if that's all good, let me keep going. Oh, and I should say, just as again a comment, that that in fact this thing is this is the exact statement, but there's an approximate version of the same statement where you say that if instead of insisting that this be 0, if I insist that this is true up to a small correction, I can guarantee that recovery works with a fidelity that's controlled by the smallness of the correction. Again, I don't want to go into that because it involves like 1 norms and 2 norms and things, which I don't want to go into. But this actually is true in an approximate sense as well as an exact sense, and that's what makes it kind of useful in the stat mech world. Okay, so yeah, the square root of E. Oh yeah, no, that's just the overall likelihood of finding that state as opposed to some other state with EK instead. But that doesn't really matter because each of these cases you'll be able to rotate back somehow. Yeah, it's a particular J, and it sort of determines. So depending which QIJ you got, you're going to have to apply a different unitary operation, right? In some sense, what this is, if you know the language of error correction at all, is this is the syndrome, right? So this is my error syndrome. It tells me what errors I detected, and that knowledge of the syndrome tells me what I should do to this QIJ to get it back into the reference form. Yeah.
So that measurement depends on how the environment and Q the details of the coupling.
Yeah, precisely.
But if I take a different prediction of the channel, then that measurement will change.
Well, yeah, the Schmidt basis will potentially change, but yeah. So is that? Yeah, I think no, I don't. I think that because if you trace out R and E, then the map from Q to Q has to be the same. So I think yeah, there aren't unitaries acting on Q. There are unitaries acting on E. So the E basis will be different. But the beauty of the Schmidt decomposition is that the Schmidt decomposition sort of undoes all of that. So different unravelings of the channel would just have different rotations between the reference EIs and like the eigenstates of the density matrix on E. Correct. Yeah, QIJ doesn't care about the thing that cares about how you purify the channel is like these bases, like at least this, the E basis. Okay, so that's all like background, and so now in what remains of this lecture, let me start drawing some pictures so. So okay, so my understanding, I should say that that all of this stuff. So now I'm going to talk about the connection to stat mech, and this discussion is in a very nice paper by Yaodong Li and Matthew Fisher, which it's one of those papers where like it's not just important, but I actually recommend that you read it because I found it fun to read. Okay, so now let me compute the mutual information. And so let me do an example where, let's say R is a single qubit, and then I have some embedding of it in Q. Okay, so I've got so these three qubits belong to Q, and my and when I draw boxes now, I mean I'm thinking about random unitaries. Is that enough random unitaries? Maybe not. Yeah, so I'm going to put in the environment as well, right? So that's going to come in, and there's going to be some random unitaries. like that. Okay. And so now what I want to do is I want to compute this mutual information that I have been talking about and see if it's 0 or not. And so to do that, what I've got to do is I've got to do 3 calculations, right? So I need to do S of R, S of E, and S of RE. So so I can do all of those in the domain wall picture. So let me so if I want to do okay, so if I want to decouple, so if I want to decouple R, then what I want to do is I want to put a plus boundary condition on that, and let's say minus boundary conditions and everything else, right? Following what Raman and Ehud both told you earlier today. So okay, so now the best way to decouple it is just to draw that line like that. Yeah. So that's the first term of these 3 terms. Now the next thing I want to do is I want to compute the entropy of the environment, and so that corresponds to putting right, once again, I'm best off doing this. And finally, I've got to do the 3rd term, which is I put a plus boundary condition, both of these guys, and minuses everywhere else. And now I ask, well, what did I do to decouple the whole thing? Well, I think if I have been thinking about this right, still the cheapest thing you can do is you can put a domain wall there, and domain wall there. Yeah, I'm not talking about a general problem. I'm talking about this specific example of, like, you know, this case. I'll come back to. I just want to give you an intuition of how these arguments would work, at least in principle. So you see that, okay, so now S of RE is basically just S of R, this domain wall plus that domain wall. So when I'm computing this thing plus that thing minus this thing, it's going to be 0, and I've decoupled and everything works. Okay. Now, fine. So does that example make sense? I mean, does the example make sense if I treat it as completely specific to this example? I drew a circuit, and let's say I made whatever assumptions I made to, like, make the StatMech model legitimate. And so I'm just saying that in this example, in this very specific example, I would do this calculation. This is how it turned out. Yeah. Yes. Correct. That's the general claim. The general claim is that if my best domain wall for S of RE is just a sum of the the 2 disconnected pieces of the domain wall, then my mutual information is 0, and I have decoupled. Okay, but now let's consider the opposite case, which I guess is what everyone wanted me to be doing at the get-go. So fine. So I guess let me do something like this. So let me just redefine what I mean by yeah, that's not going to work, is it? Okay, fine. Let me make this model kind of really stupid, like call this is so Q is just these 2 guys, and everything else is the environment. Okay, so I'm going to change. This is going to change where I put my pluses and minuses in the boundary. But now you can see that if I now try to compute S of R, S of RE, then I don't want to make this domain wall and that domain wall, right? Instead, I want to connect the domain wall up like that. And so that's a much smaller number than, so that's 2, whereas S of E gave you 3 and S of R gave you 1. And so in this example, the mutual information isn't 0 because because the domain wall for RE is not just the domain wall for R and the domain plus the domain wall for E. It closes a different way. And so that means that in this example, you know, R and E don't decouple and the error is not correctable. What are you asking? Yeah, so S of RE is the entanglement of the entropy of the density matrix in RE, right? Okay, and to compute that using the StatMech model, what I do is I put in trace boundary conditions on Q, which I'm calling trace boundary conditions minus. Yeah, precisely. Yeah. And that just comes out of like putting the pluses and minuses the domain wall construction, right? So these guys get the identity permutation. These guys get whatever permutation corresponds to the entanglement calculation. And what you're trying to do is you're trying to make a domain wall between these two permutations. And if these plus regions were small and far away from each other, then you just close them separately. But when they're big, the best way to compute the best way to like put the domain wall for this system is just send it up like that. And so this is a much smaller, so this number is now much smaller than the sum of those two. And so mutual information is positive, and decoupling doesn't happen and the error is not correctable. Okay? Yeah.
So this is just saying like Q was not a large enough Hilbert space to like sort of make the state more redundant.
Yeah, for a random circuit, that's kind of all it is, really. It's like not a big enough Hilbert space for the circuit depth or whatever. Yeah, so I mean, so in general, it's a function of both the Hilbert space sizes and the circuit depth. You know, it's a question of where you want to put these domain walls, and that depends on both those parameters. But yeah.
This is supposed to be a monitor circuit?
No. This is just some unitary quantum circuit which also has a StatMech description for the entanglement, right?
I thought
the monitoring.
I thought the cases
Yeah.
The two phases are examples of two phases which were.
Let me come back to the connections. That right now you should really think about me as asking a kind of related question about coding, but a somewhat different one because I have no projective measurements in my universe. I'm talking about a more basic question, which it's sort of independent of post-selection problems and any of that stuff. I'm just asking in a unitary circuit, where is the information encoded? And then there's a second question, there's a second layer on top of that, where I can put in measurements. And if I were to put in measurements now, I would do what Ehud did in his lecture, which is I would put in the measurements, as a measurement channel. I'd have a more complicated system where I could once again start computing these quantities.
But somehow with measurement, unitary with measurement, you can relate to how big the E versus Q relate to this kind of stuff.
Yeah, that's right. So it's a bit involved, but yeah, because you have to deal with the fact the measurements are sort of very specific channel. But yeah, morally it's the same thing. Right, morally, what you're doing when you put in measurements is you're introducing additional qubits that keep track the measurement outcomes, and you're introducing some error channel that's like the environment, and you're asking the same question of whether you've decoupled you've decoupled your system, which now includes the classical measurement outcomes from the environment. But yeah, so this is just the general structure of how in quantum channels decoupling works or doesn't work, and sort of information either leaks out or doesn't leak out. Okay, fine. So in the last 10 minutes or so that I have, let me just draw a couple of more pictures. So I'm going to do it. Yeah, let me do that over here. So it's and so the way I drew this thing initially, I wanted to make everything on the same time slice. So I wrapped this leg around in order to move it over here. But right now they've converted into StatMech language. There's really no need to do that. I can just put in the boundary conditions over here. makes the diagram a bit simpler to draw. And now what I can do is I can rewrite this diagram. If I assume that now I have some system. Now let me assume now that I have a system where I have some small reference space, which is down here, which I'm going to give periodic boundary conditions to make the drawing simpler. And then it gets encoded via some unitary circuit in a much bigger system, and that's going to look sort of like this. It's like you have your little system there, you have your big system up here, and then you have some StatMech model living between these two boundaries. Yeah, this is our this is Q. And now what I'm going to say is I'm going to think about a specific model of how the system interacts with the environment. And that's just, I'm going to say that the environment just eats up some contiguous set of degrees of freedom in the system. This is not meant to be a particularly realistic model, and I could make these non-contiguous as well, but this is just a simple model to think about. So the environment comes in and let's say it takes away these degrees of freedom, it just swaps them out, let's say. It depolarizes them. So they get erased. And now the question is my information still inside the system? Okay. And so now I can draw that question in terms of the following three diagrams. So the first diagram I more or less already have up. So there, I'm just computing. So I have red boundary conditions on R, green boundary conditions on Q. I'm sorry, I'm just using minus and plus arbitrarily from one writing to the next, and my domain wall is going to cut things out somewhere like that. I mean, okay, there are certain restrictions in what it can do, but it's gonna cut things out. It's gonna cut the circuit somewhere.
Are you considering Ising variables or before there were permutation?
Yeah, let's assume they're let's assume in general they're permutation variables. It's not the key. Okay, so one thing I'd say is for certain questions like talking about universality classes of phase transitions, it's very important what the symmetry is. But for questions like this about the properties of the volume law, the unitary dominated phase, it's completely irrelevant essentially what the symmetry is. The only thing that really matters is that it be a discrete symmetry, so its defects are domain walls.
Then you just take second Renyi and
you could, if you wanted to, you could do the 10th Renyi entry and become something else, but it doesn't, what I'm saying is sort of agnostic to what these degrees of when I say minus and plus, I'm just saying this is one boundary condition. This is a different boundary condition. It could be two out of an infinitude of boundary conditions. It's just they're two different boundary conditions, and so I need to put a domain wall between them somewhere. Yeah. Yeah. Yeah, they're going to be quantitative. They're going to be quantitatively important aspects to the fluctuations that do care. But for the sort of the coarse-grained, basic picture of what the domain walls are doing, and what error correction means in terms of domain walls is completely agnostic to these details. So you can take a fairly coarse-grained view of what's happening. And so, okay, so now I do the rest of these calculations, right? So now I can. So the problem with blackboards, you don't really have a copy and paste function, which I'm beginning to regret. Okay, but here's your reference. Sure. Yeah, I know. Fine. So okay, so this is the reference. Can you see the cylinder? Yeah. Okay, just imagine it's there for now. And then on the next one, I'm going to draw it better. I haven't really included this is just like S of R. So I haven't introduced E yet because Q and E are being treated the same way in this calculation, but it's going to matter now. Right, so now I've got to put the the bandwidth. Now I'm going to trace. I'm going to compute the entanglement of E. And to do that, what I do is I have the trace boundary conditions on most of Q, but then I have a different boundary condition on like this region. Okay. The bottom is now, so here the boundary conditions, the bottom and the top were different. Now I'm computing S of E. So the bottom, so R and Q are being treated the same, so they have the same boundary condition. And so, okay, so now this guy is gonna connect up something like that. And now finally, what I need to do is I need to compute the R, yeah, the RE thing. And so now I need to put, well, let me choose yellow boundary conditions on R, yellow boundary conditions on E, and green boundary conditions on Q. And now you can see that depending on the details of the sizes of these guys and the depth of the circuit, there are two ways this could close. One way to close is to draw a domain wall over there and something like that. And this would be the case where error correction does work. But the other thing you could do if E were bigger is that you could close the domain like that. And if you close the domain like that, then that means that decoupling hasn't worked, the error isn't correctable. So a transition where you erase enough, where you have enough errors, or you've removed enough qubits from the system that error correction doesn't work, corresponds to a change in the topology of this domain wall, and that's how it shows up. That's how the failure of error correction shows up in the StatMech model. So that's the StatMech picture of when error correction is possible and when it isn't. And so okay, so this is the basic idea. And I'm actually well, I'm out of time. I'm pretty close to done. The one thing I wanted to talk about today that I didn't get to was the Hayden-Preskill treatment, the black hole paradox, which is sort of almost a trivial extension of this. But I'll probably just talk about that in the first 5 minutes of tomorrow's lecture. Okay, fine. Okay, do you guys want to stop another 5 minutes of this? I guess you'll have to. Okay, so let me do a lightning discussion of Hayden-Preskill. So this is a pretty famous paper, but again, it's one of those papers that I actually do think are worth reading. Okay, so what happens this instance in Hayden-Preskill is that Alice wants to get rid of some qubits and wants to protect them from all possible intruders. So she sticks them in a black hole. So this unitary is supposed to be a random scrambling unitary that encodes Alice's state inside a black hole. Okay, it's like supposed to be some isometry. And normally I'd say the black hole started out with 0 legs down here. So it's just an isometry. But the key point here is that the black hole is actually an old black hole. So it's entangled. It's not just in a pure state. It's entangled the radiation that's been coming out of it since the beginning of the universe. So in fact, a more accurate picture of what the black hole is this. Okay, so it's like it's part of so the radiation in the black hole is part of, it's like in a bell pair with other stuff in the universe, and so you want to take the perspective of an extreme paranoiac. So Alice is really worried about any hypothetical Bob that could get the information out somehow, and and so the idea is there's some hypothetical Bob out there who's been just collecting all the radiation from the black hole since the beginning of the universe, and now holds the purification of the black hole in his hands. Okay, seems dangerous. Okay, but so now now you have some state on the black hole after it's been interacted with, and so one thing I'm going to do is, in order to talk about fidelities under entanglement, I'm going to do the same thing as I did previously. I'm going to purify Alice's state with a reference, and so Alice. So this is reference of Alice. These legs. These legs are the black hole. I'm going to draw prime because it's a black hole after Alice has interacted with it. These guys are the reference belonging to the black hole. Okay, and yeah.
That guy is the environment.
Yeah. I mean, it plays a kind of funny role, right? Because it carries. So the state has been, the black hole's been emitting radiation since the beginning of the universe, and so it's actually highly entangled with the outside universe, and so Bob has access to all of this stuff. So it's some kind of environment. It's not exactly the same environment that I had last time, because I wasn't thinking about like a giant bell pair like situation last time. Okay, so now what happens next in the story is that some of the radiation leaks out of the black hole. Some more of the radiation leaks out of the black hole, and so effectively what that corresponds to is a few more qubits become accessible to Bob. So you have a situation like that. And this is a final black hole after like more radiation has come out of it. And this stuff now has been incorporated into RB. And okay, so now the claim is that the claim I want to make is that so after a few qubits, after RA worth of qubits, have been emitted. So after this situation has been obtained, the following statement is true, that Alice has now decoupled from what remains of the black hole. Okay, and because Alice is decoupled from what remains of the black hole, it follows that Bob now carries the purification of Alice's state, and so Alice is now, Alice's information is all sort of Alice's reference like completely leaked out to Bob. And so how do I make this argument? Well, I make it exactly the same. I'm not going to do it explicitly because you can sort of see how it's going to go. But I've got to compute these. I've got to compute this mutual information the same as I computed these other mutual informations. And I'm going to find that at some point, when enough radiation has been emitted, the domain wall flips its direction, and the mutual information structure changes, and you decouple. Okay, so that's an interesting application of these StatMech ideas that sort of it's much easier to think about with the StatMech picture than I think than it was before. Okay, so that's yeah, precisely. Yeah, that's the point. So because it's decoupled from what's left of the black hole, Bob. So basically, the global system universe like some kind of giant bell pair between Alice and Bob, and then so Bob can, so any information that Alice sent in here would be teleported over to Bob, and Bob would be able to reconstruct it. Order RA additional qubits, because immediately after Alice dumps her qubits into the black hole, it's clear that B double prime is like the biggest of these systems, and so these guys are gonna decouple. But then once order 1 qubit, or if Alice sends in order 1 qubits and once order 1 qubits have gone, then you have decoupling, and then there's nothing. So that's the Hayden-Preskill argument. It's sort of it's a bit counterintuitive, but like you can see kind of naturally that it follows from this framework.
Sorry, does it resolve the black hole?
It doesn't resolve the black hole paradox. What it does is it tells you that right. So you might have thought that if you dump information into a black hole, the information takes a really long time to come out, right? In a way that's like reconstructible. you might think that, information takes until the end of the universe or whatever to come out. What this argument tells you is that is completely wrong for an old black hole. In fact, the information comes out almost as quickly as you put it in. So it comes out in basically order 1 time. The thing that's difficult is not the information, it's not information theoretically, the information coming out. The thing that's difficult is constructing the recovery map that I, gave you from the Schmidt decomposition in a totally non-constructive way. So that's the thing that makes it difficult to extract information from a black hole. It's not a fundamental thing about, it's not a fundamental information theoretic thing in this picture. It's just a computational challenge, but maybe a very, very difficult computational challenge. Yeah, exactly. So I want to think about the black hole as scrambling in order 1 time, but you want to think about time as being measured in like units of black hole scrambling somehow. Yeah, that's the important thing. So when order 1 qubits have been emitted after assuming good scrambling, then this argument holds. Of course, if the scrambling were not good, then you'd have to make a local unitary circuit, let's say, and then you'd have to, or sort of an all-to-all unitary circuit of some kind, and then you'd have to do that stat mech calculation. Yeah, I think that's right. And you'd probably be able to get that from like just writing this thing as some kind of all-to-all, random unitary circuit. Yes, you probably need order log n time in order to like just scramble the information. But I mean, I'm actually not sure that you need order log n time to get the information back out, because if it's not scrambling so well, then maybe it's, if it's not scrambling so well, then it's very unlikely that the qubits that you put in would be the ones that came out. So that's right. You probably do need to wait for the scrambling time. Yeah, thanks. Yeah.
That statement, like the
Mhm.
Is that a restatement of monogamy?
I've honestly never been able to figure out what monogamy of entanglement is. So yeah, no, you can think about it like that, but I don't know if that's a legitimate interpretation of it. But it certainly feels like it. Yeah.
So to be really maybe pedantic, almost like the statement only holds for the mutual information statement. It should not hold for like any versions of information.
Correct.
So we need to still think about the replica limit in this, like
correct. That is correct. So to make these arguments cleanly, you need to be talking about the von Neumann entanglement entropies to make the mutual information out of. And so it's a replica theory. But then, I mean, the key point really is that as far as we can tell, it's a replica theory with a discrete symmetry breaking pattern in the replica limit. And so it has domain walls the replica limit as well. And that's the only feature of the theory I needed in my discussion. So so I'm not treating that as a particularly dangerous step, but that's correct.
But I mean, in general, in principle, that any 2 versions can violate SS from
Yes, I'm not really an expert on like what's known and what's not about Rennie versions of mutual information, but I don't really. So I mean, there are versions of this that can be proved for like, so in approximate decoupling, there are results that you can show that if the purity of so if the norm of, if the 1 or 2 norm of rho RE minus rho R rho E is less than a certain amount, then things work. But as I said, that involves a lot of futzing about with like the precise analysis of like various different norms. So I don't, but I mean that's correct. So if you wanted to be careful, you'd want to be careful. Yeah.
What is the need for this bulk is a capture all the radiation before the circuit? If you did the purification, I think of the black hole analogously to that purification where you just start with like unentangled qubits, you just wait, not having collected any previous qubits, but just wait long enough later and then.
Yeah, if you had a new black hole, then you'd have to wait for like half the black hole to evaporate. Whereas here, the key point is, and that would not be surprising, right? Because that's sort of I think the naive expectation you'd have that you put in information to the black hole and it would stay there for order the life of the black hole. the surprise is that that's not true in this instance. If the black hole is more than half evaporated, then it's like it doesn't hold information for long at all. Yeah.
So the structure like kind of reminds me of like Hayden-Preskill formula and like.
Mhm. Yeah. Absolutely.
So it somehow is this thing that like these circuits with different bond conditioning code, well, in some ways derive ADS-CFT.
Yes, I'd say that not just for like what I was talking about today, because I think that's a very boutique example of it, but just like even the entanglement calculation that Adam Nahum did like 6 years ago, like even that was basically just it was really, you can think about it as a derivation in the random circuit model of the Ryutake-Yanagi formula. Min-cut is Ryutake-Yanagi. But sort of, I mean, I guess I don't.
What do you do for the field design?
Yeah, I mean, I guess that's right. So you can think about. So I mean, the point is, so there's all this discussion which I haven't prepared notes on, but like there's this idea of like the bulk and the boundary of a. So you want to think about the bulk and the boundary of a black hole as like some kind of random tensor network with like some kind of tree-like structure inside, where you have legs in the bulk coming out like that, and then legs in the boundary that yeah, and so you can think about either one or the other as physical, and so one of these encoding in the other, and so this is a discretization of that field theory picture, and the holography really is the fact that that the physical degrees of freedom live on the boundary of your random tensor network.
I mean, the strange thing about it is like there somehow the fact that it's AD space is crucial because that's what encodes conformal symmetry
Yeah.
of in the gravity.
Yep.
While here the structure of the tensor network is completely sort of a detail.
In the sense that some version of this result is true for like a very wide variety of random tensor networks, right? Yeah, that's right. Yeah. So yeah, for the random tensor network versions of these results are like quite general. I mean, I guess, yeah, I don't know enough about holography to comment much further on like on this. But if anyone has anything to say. Yeah.
It's worth just mentioning there's no ADS case here, but there's also no CFT.
That's also true. Yeah, this is like non-ADS to non-CFT correspondence. Yeah, precisely. Yeah, it's the membrane picture, which turns out to be. I mean, it was first found by Ryutake Yanagi doing something totally different in a rather restricted setting, but it seems to be like a much more general thing. All right, thanks.